Hi everyone, for this lesson we're going to look at an extension of converting mass into moles, and that is looking at calculating the mass of products with a given mass of reactants. And so the best way to teach this is by example. Here we have a question where we have 32.6 grams of potassium and it's going to react with excess oxygen. How many grams of K2O is produced? And so first of all, what we need to consider is a balanced reaction. And so we can see this balanced reaction here would be two potassiums. We have half an O2 gas molecule going to K2O solid. If you like, we can multiply all these stoichiometric coefficients by 2 to give us the 4 potassium plus O2 going to 2 potassium oxide. Now, in order to be able to work with these equations, we have to calculate the number of moles of potassium. And so, first of all, when you calculate the number of moles, forget the stoichiometry, at least for this first part. And so we use this formula: number of moles equals mass over molar mass. And so if I want to work out the number of moles of potassium, I have the mass of potassium, which was 32.6 grams, divided by the molar mass of potassium, and from my periodic table that's 39.10 grams per mole. And if I go ahead and work that out on my calculator, I'm going to get 0.8338. And that would be mole. Now at this stage, I just leave that on the calculator, and I don't worry about significant figures at this stage. The final answer you need to report to the appropriate number of significant figures, but if you start reporting everything at every step with what you think the right significant figures, you'll get a rounding error. So just wait till the final step before you report to the correct number of significant figures. So I'll leave that in your calculator there. My next step is to go back to the equation and have a look. And so either one's fine to use. And what this is saying is that two potassiums react with half an oxygen molecule and give 1 molecule of potassium oxide. Okay, so what I have to do is consider the molar ratio of these species. So the best way to do this is the number of moles of, I like to put what I'm interested in finding up the top. So number of moles of potassium oxide divided by the number of moles of potassium, because I actually know this, equals. Then I go back to the equation and I look at the stoichiometric coefficients. So here, this would just be a 1. There's a 1 in front of here. So it would equal 1 divided by 2. And so if the number of moles of potassium oxide is up top, then you use the stoichiometric coefficient of potassium oxide up the top. Okay. Similarly, the number of moles of potassium is down the bottom, so I use the stoichiometric coefficient associated with that species down the bottom. Okay. I could have used this other equation with the 4 and the 2, and if I did that, I would have had a 2 over a 4, okay, which again is just going to be a half. And so this should all make sense, because really all an equation does is it just shows you what the ratios are. And I know we're looking at these molecules. In reality, you would have billions of these molecules, or millions, or hundreds of billions, depending on the quantity you've measured out. And so all it's saying is, instead of having to put, say, 2 billion here, half a billion here, 1 billion here, these stoichiometric coefficients are just giving you the ratio. Okay, and so that's all balancing equations really means, is that we're reporting how much of one thing is relative to another thing. So back to our equation. From here, I can rewrite this. So if I just look at the number of moles of potassium oxide divided by the number of moles of potassium being 1 over 2, I can multiply both sides by the number of moles of potassium, and that would give me that the number of moles of potassium oxide is going to equal 1/2 the number of moles of potassium. And again, if we go back here, that's what we can see this is happening, is that this is half as much as this, and this is half as much as this. But it's very important you follow this procedure, because often students will get mixed up and say this is twice, sorry, this is half as much as this, when it's really twice as much as this. Okay, so from here, the number of moles of K2O is going to equal 1/2 times what we've already worked out for the number of moles of potassium. And again, I just have these values on my calculator, and so I divide that by 2, and this gives me 0.4169, and that's to 4 significant figures. Okay, it doesn't really matter too much what you reported. I just, out of habit, write down 4 significant figures. But again, it's the final answer that has to be in the correct number of significant figures. So from here, I then want to complete the question by looking at the mass of potassium oxide. So given this number of moles, I can again use this formula, number of moles equals mass over molar mass, and rearrange this. So I get mass equals number of moles times molar mass, and again that's going to be the number of moles of the potassium oxide times the molar mass of the potassium oxide. And so the number of moles we just calculated, which is this 0.4169 mole, and then I've got to multiply by the molar mass of potassium oxide. And so there's going to be 2 lots of those potassiums plus 1 of those oxygens. Okay, and so when I multiply all that out, again I've maintained that value on the calculator there, and so when I go to multiply all this out, I just use that first value, multiply by parentheses 2 times 39.1 plus 16, close parentheses, and then I have my final answer is 39.27 grams. But if I'm going to report it to the correct significant figures, I'll look at the original question, and I said it was 32.6 grams of potassium initially. That's 3 significant figures, so my final answer is actually going to be 39.3 grams. Okay, bulk of potassium oxide. So that's a simple method of calculating the grams of product from the grams of reactant. And so just to walk back through the steps, you really have to get a balanced equation worked out first. If you don't, it won't be in the right stoichiometric ratio when you're trying to calculate things. So the first thing is to get the equation worked out first, then always come back to relating the ratio of product to reactant in terms of numbers of moles, and use the stoichiometric coefficients. So if this number at the top refers to the stoichiometric coefficient of whatever this is up the top, and similarly for the bottom ones. And so you have that ratio, then you can multiply it out, and so we get this expression, and then from there it's just back converting from the number of moles that you've just calculated in the previous step, back converting it to mass using the molar mass of the species. Now, again, when you notice when I worked out those molar masses, I didn't take into account that it was 2 potassiums here, or you know, I guess 1's there anyway. But you don't have to, when you're working out the molar masses, don't take into account that, because these 2's and 1's and things are taken into account in the mole ratio. Okay, but you do have to take into account the little numbers, because these subscripts refer to the molecule as a whole. And I'll just leave it there. Thank you.